All right, so we're going to figure out how to calculate the pH of a strong acid, and you're going to love this because all you need to do is figure out the molarity of the strong acid, and then you know your pH. You can take the negative log of it. So, what do we have to do first? Well, we have to know what our equation is and what we're actually seeing here. In this case, they give us hydrochloric acid, and in all cases, whenever we're trying to solve a problem and we want to write an equation, what do I tell you we do? We throw it into water. So we're going to throw this into water. And then we're going to write what happens here. This is aqueous because, again, it's being dissolved in water. And I'm going to put a one-way arrow because we know it's a strong acid, which means it's going to 100% dissociate to this side. So on this side here, we're going to end up with H3O plus because remember, this guy right here, this is acting as the base, this is acting as the acid. What do bases do? Well, they grab hydrogens and they become H3O plus. And then what gets left over? We have the Cl minus that's left over here. And this is our overall equation. What we do know is that if we start off initially with a certain concentration right here, then at the end, we're going to end up with none of this, and all we're going to have are these concentrations over here, which is our final. So in order to do this, our first job is we have to figure out what is the concentration of HCl to begin with. And they're a little bit meanish here because they give us 758 milligrams, and they give us 220 milliliters. So our guiding principle, and I would always suggest this when you're trying to figure out what to do, I would always write what the molarity equation is. Molarity is equal to moles per volume. We know what our volume is. And by the way, our volume has to be in liters, unless both our moles and our volume are in milliliters. We can do it that way if we'd like as well. But in this particular case, I want to first get from this to moles. So how do I do this so I can plug it into here? Well, I start off with our little train track system here, and I'm going to go 758 milligrams of HCl. And I want to get rid of the milligrams and make it into grams because that's what molar mass is typically written in. And don't we know there's 1,000 milligrams for every 1 gram? That gets rid of our milligrams, and now we're at grams, which is healthy for us. And then we need to look up what the molar mass is, and we know for HCl, it's 36.454 grams for every 1 mole, and that cancels out our grams, and we end up with moles of HCl. I kind of got lazy here writing HCl in all these cases, but I should have. And when we did the math, we end up with 0.020793 moles of HCl. Now, you may think to yourself, well, wait a second. All we had right here were 3 significant figures. Shouldn't I cut this off right here? And the answer is yes, but here's the rule. We tend to in order to make our problems more accurate, we do our rounding on the very last step. So we're going to keep this monstrosity in here, but we know that this right here is going to go right here. So the only thing we have to do for the volume is look up here at our 220 milliliters and realize we cannot have a volume in milliliters in this. So we're going to do the same thing via mathematics. We're going to go 220, and I believe that there's a decimal in there sure is, milliliters, and we're going to divide that by 1,000 milliliters for every 1 liter, and that's going to give us 0.220 liters. So right here we have the two numbers that we have to plug back into our equation. We have the moles and we have the liters. And so if we put both those into our equation right up here, we're going to end up with 0.020793 all divided by 0.220 liters. So this is moles divided by liters. And when we do that, we end up with a molarity of 0.094514 molar. That is the molarity of our HCl. Now, here's where this gets really, really great. So if we know what our molarity is for our HCl, that's our initial amount right here. I'm going to do a different color just in case it's getting a little bit crowded or congested. This number right here, I'm going to put as my initial amount, 0.094514. And I know that because it's a strong acid, all of it's going to go to this side. All of it, all of it. So at the end, I'm going to have none of this. Now, initially, I have none of this, and I have none of this. But at the end, I'm going to have this amount completely dissociated. Now, remember, the way this works is that for every one of this right here, For every one of this I lose, I gain one of these, and I gain one of these. So for every 0.094514 of this that I lose, I will gain that same amount here and here. So if I want to, I can just put the numbers down below here and write 0.094514 and 0.094514 right here. Now, the truth is, both these numbers right here, these are the molarities at the end or at equilibrium of H3O plus and Cl minus. But we don't care about the Cl minus. We only care about the H3O plus because they asked us in this problem to solve for pH. They did not ask us to solve for PCl. So all we have to do is take the concentration right here and take the negative log of that. So let's write another equation down here. We're going to say pH is equal to the negative log of my H plus concentration, or H3O plus concentration, however you want to write it. And when we do that, we're going to have the negative log of 0.094514. And when we do that, we end up with a pH of 1.024538. And I've grown weary of writing stuff. But what we do need to be aware of here is we have to do the correct number of significant figures. So I'm going to go back up here for my sig figs. Don't I have 3 significant figures right here? So that means when I look down here at my number, I'm only allowed to have 3 significant figures. Now remember, we do not start counting from here. We start counting after the decimal. So these are the 3 sig figs. And you see how this number right here is going to round this number right here up? So our final answer is going to end up being 1.025. Those are my 3 sig figs. This is the answer for this problem, and hopefully it has been helpful.